Good afternoon. So as you know, the midterm will be on Friday. So today we devote this lecture to the preparation for the midterm. So sections covered in the midterm are 7.1 to 7.8. 8.1 is not covered. Okay, that is not included in the midterm. Okay, let's concentrate. Basically, the big umbrella topic that is covered here is techniques of integration. So today we'll solve several examples, talk about some of the more important techniques. To start, let's review. So the first technique that we looked at is integration by parts. So that's section 7.1. So I'll give you an example of that. You should know this very well. And we have trigonometric functions and the duality of sine, cosine, tangent, secant, section 7.2. And we have trigonometric substitution. And we have partial fractions. So this is 7.3, 7.4. Okay, so let's look at these first. So let me give you an example of something that is not exactly obvious, right? Sometimes you have to use several methods. So e to the 2x minus 1, the square root of. So in this case, we're going to use, what is not listed here is a couple of things. So substitution is not listed because technically we did it before the first midterm. But of course, we have to use it all the time here in combination with other techniques. So you should know substitution. So I put it here. So let's not forget that. So here, the substitution is non-trivial. We take this whole radical and denote it by u. Okay. So now we want to evaluate the differential. So we differentiate this expression, this definition, by using the chain rule. So first we differentiate the outer function, which is the square root. And then we have to differentiate the function that appears inside, which gives me 2e to the 2x. And I simplify it a little bit. Sorry, dx. Okay. So let's now try to use this information to substitute into the integral itself, right? So we write down the following expression. We have dx times e to the 2x minus 1. This is the expression that appears under the integral. And I'm going to extract it from this expression. Okay? So I have to multiply both sides by e to the 2x minus 1. So I get du times e to the 2x minus 1 and divided by e to the 2x. Okay? So this is substitution, but kind of used at a higher level. Question? No, so you have to consider the left-hand side and the right-hand side. I want to one second. Dx. Yes, so let's take this expression and multiply it by the following combination. E to the 2x minus 1 divided by e to the 2x, okay? Both sides, left and right. On the left, I'm going to have this. And on the right, I have dx, this cancels, and the square root cancels, and I'm left with this. Okay, so this is the transform. This is the operation that I use. Is this clear? I take this and this and multiply them both by this expression. So on the left-hand side, I have du times this whole thing. This is easy, right? On the right, I have to multiply this by this. So e to the 2x cancels. E to the 2x minus 1 gets divided by the square root. So what is left is e to the square root times dx. Question?
Yeah, how did you figure it out? Was it just for this problem?
Oh, this is because I want to recreate this expression. Okay, so this is what my ultimate goal is every time with substitution. I want to express everything under the integral in terms of my new variable. And I can see that square root appears here, and it happens to be here too. So I just modify this expression to get it to this form. Okay, and so far, okay, I got this on the left, but on the right, I have both u and x. So my job is not complete yet. So what am I going to do? I'm going to try to continue this to express everything in terms of u. How do I do this? Let us write down the definition again. U squared equals e to the 2x minus 1. So e to the 2x minus 1 is expressed easily in terms of u squared. How about 2x? I can say that e to the 2x is u squared plus 1. So I can continue here, and I have du times u squared, and in the denominator I have u squared plus 1. Okay? So I expressed the whole thing in terms of u by a clever usage of this definition. Okay? Now I can rewrite my original integral in terms of the new variable. So I get u squared du u squared plus 1. Okay. So now, is this an easy integral or not? You can say that this is u squared plus 1 minus 1 du u squared plus 1, right? Plus and minus 1. We already used this trick before. And this gives me 1 minus 1 over u squared plus 1. And now I can recognize something that is in the table of integration. So it's u minus arctangent u plus c. And going back to the original definition, e to the 2x minus 1 plus arctangent of the same thing plus c. Okay? Why is it plus c?
No, plus 10, plus 10.
Minus. You're right. Thank you. Okay. So I thought I would shock you. This is as hard as it gets. Okay. So this gives you the upper kind of expectation. Okay. If you can do that, you get an A+. Okay. So easy, right? So from now on, everything is going to be more, kind of not inspiration driven, but perspiration driven, so to say. Questions about this? Okay. let me give you this example. Also techniques of integration. So square root of x, 1 plus x dx. How about this one? Okay. So here, let's say square root of x equals u. Okay. Now we can say dx over 2 square root of x equals du. Or we can resolve it for dx, 2 square root of x du, which is 2u du. And x equals u squared. So by doing these operations, we can rewrite everything in the integral in terms of the new variable. So what is square root of x? That's u. What is dx? Dx is 2u du. What is 1 plus x? That's 1 plus u squared. Okay. 2u squared du, 1 plus u squared. And then I say dot, dot, dot. It's the same integral we just took. Right? This is equal to 2u minus arctangent u plus c, or 2 square root of x minus arctangent square root of x plus c. Question? I'm sorry? Oh, this integral is the same as this, so we can just look at this line. When I see 1 over u squared plus 1, that's the antiderivative of the arctangent. Okay? So you have to remember this very well, the ones that appear in the table. Question?
The value of 2u du?
Differentiating the left-hand side and the right-hand side, I got this expression.
Yeah.
And then I expressed dx from here. So dx is equal to 2 square root of x du. And what is square root of x? That's u.
Oh, okay.
Yeah. So we go back and forth all the time. We always refer to the definition. Okay. Good. So now something different. Let's consider a straightforward application of one of these rules. So let's look at the following example. X squared e to the 3x dx. Okay. Here's only one rule that we use. This is integration by parts, but we'll do it twice. Okay. So I said u equals x squared, and v prime is e to the minus 3x. So actually, let me write it like this. Okay. So now I have a product, and it's more straightforward to think of the differentiation by parts. So I assign my variables, my new functions u and v. I differentiate u, and I integrate v. And that completes the first step of this method. So I have uv x squared e to the minus 3x over 3 minus 2/3 x e to the minus 3x dx. Okay. So first it's a cross product u times v, then minus integral of these two. Now I look at it and I say, and I ask myself, did it get better? Or did it get worse? Okay. And I can see that I started with x squared times the exponent. I ended up with x times the exponent. So in my opinion, it gets better. Good?
Should be a plus 2/3 of the integral.
Yes, thank you. Okay, so, but again, I have to apply the rule one more time. So here I said u is x, and v prime is e to the minus 3x. U prime is 1, and v is minus e to the minus 3x over 3. And I continue to write this. Plus 2/3. So I'm going to leave the 2/3 outside the bracket. And now I have minus x e to the minus 3x over 3 plus the integral of e to the minus 3x dx over 3. Did it get better? Yes, completely, right? This I can integrate. It's just a straight exponent. So I'm only one step away from the answer. Okay. Questions? Question?
Can you give us any involving sine, cosine, like multiplying? Kind of like repeating ones that
Repeating.
the ones that. Yeah, no, forget it. I'll expect it.
Oh, he's talking about the ones where you gotta like put them all on one side and then.
Oh, when you arrive at the same type of oh yes. So this happens only more or less. The most common example is when you have an exponent and a sine or a cosine. Okay, and if you've done it once, okay, you know them all. You just do it twice, and see here the power. You start from x squared. Here you have x, and here you have no x. If this was a sine or a cosine, you would have like sine, you would have a cosine, and you would have sine again. So then you denote, and if you made the full circle, you denote that by I. This is I, and then you solve for I. After you solve for I, you don't forget to add c, okay, plus a constant. Okay? That's all. And let me show you another example. So I want to use my time wisely. So let me do a couple of examples on the improper integrals. Okay. Improper integrals. So let's look at the following. So how do I know that this integral is improper? One of the limits of integration is infinity.
Yeah.
Okay, so I can immediately rewrite it as a limit of this. Okay. So now I can handle this as integration by parts again. Okay. So let's write it. Sometimes I don't want to carry the limit sign with me all the time, and I just want to evaluate the proper integral first, and then I use it here. Okay. So let's do this integral. We just did it. It's really easy. By parts. So this is given by x minus x e to the minus x from 0 to t plus e to the minus x. Okay, so I use the substitution. I substitute the limits of integration. It's a proper definite integral. So I have minus t e to the minus t minus 0 minus e to the minus x, evaluated again at the same limits. So I have minus t e to the minus t minus e to the minus t plus 1. Okay, so I calculated this object, the proper definite integral. And now I can use this expression to calculate the limit. So sometimes it's easier to do it step by step. Okay, so I did all the work. Now I go here, and I say this is the limit as t goes to infinity of this expression, minus t e to the minus t minus e to the minus t plus 1. Okay, so now L'Hopital. Okay, so we won't be testing L'Hopital's rule directly, but it happens all the time in these improper integrals, right? So you may be exposed to like not the most advanced cases of the L'Hopital's rule, but you should know what it is. First of all, when t goes to infinity, what happens to e to the minus t? That's the easy one. So this one goes to 0. I don't have to worry about it. So what is the limit as t goes to infinity of minus t, or let's just say t e to the minus t? So t goes to infinity, e to the minus t goes to 0. So we have an indeterminate product. Okay, so we write it as an indeterminate fraction, where both of these things go to infinity. And then we apply L'Hopital's rule by taking the derivative. And this is easy, right? Now it's easy because e to the t goes to infinity, so the whole thing goes to 0. So this goes to 0 by L'Hopital. So this thing is equal to 1. And this is the answer for this whole improper integral. Questions? Okay, I'm going to do another one, a slightly different one. Does this, does the following improper integral converge or diverge? Okay, so I have to use a comparison. I cannot integrate this, but I can use a comparison test. So this is something that we should remember. If I show that this is something that is smaller than a converging integral, then it's also going to converge. So let's try this. We said we'll look at the expression under the integral, and let's see if we can bound it by something that we know. You know that what does the sign x do as x goes to infinity? It goes up and down between -1 and 1. It can never be smaller than -1. It can never be bigger than 1. Okay, so this whole thing has got to be less or equal to 7 over x squared, right? Because this guy, sometimes it's negative, sometimes it's 0. It goes up to 1, and it can never make this numerator greater than 7. Do you see this? So this thing is less than this. And this is an easy function to integrate. In fact, you may remember the answer. Does this, when I integrate this, does to infinity, does this converge or diverge? this converges because the power is greater than 1. Okay? If it was 1 over x or 1 over square root of x, that would diverge. If this power is greater than 1, it converges. If you don't remember that, you can check it. So consider the integral from 5 to infinity, this 7 over x squared dx. So this is the limit as t goes to infinity. 5 to t 7 x squared dx. The limit, so I have 7 minus over x from 5 to t. Okay, so I have minus 7 limit as t goes to infinity of 1 over t minus 1/5. Okay, so what's the limit? This goes to 0, right? I have minus 1 over 5 times minus 7, 7/5. So this guy converges. Therefore, the original integral converges too. And let me write it down, comparison test. Okay, so look it up. Question.
When you do the comparison test.
So the method to show this is the comparison test.
Yeah, but if we say it converges,
By
you
compare.
have to give the point, like the number at which it
So if you give me the right calculation like this and say nothing, I'll be happy. If you make a mistake somewhere, but say comparison test, I'll give you a point, right? So it doesn't hurt. Because this, you may make a mistake here, but if I know that you know, it helps you. It helps you, it helps me to grade it. Question?
What if we just write the first thing that you say? Like, if we don't prove it, will we get the point?
Well, everything helps, right? Everything helps. Try to get the whole thing.
Okay.
Please, I encourage you to do the whole thing. Okay. Partial fractions. So there are 4 types of partial fractions. And please remember what you do for each. Okay, linear factors, non-repeated, linear factors repeated, non-linear factors non-repeated, non-linear factors repeated. So this first example is as follows. It's like this. So we try to factor out the denominator. And of course, you can try to solve this quadratic equation. You'll find it has no real roots, right? Or you can just remember that x squared plus a constant is an irreducible quadratic factor. So there's nothing we can do about it. So we have one linear factor and one quadratic factor. So let's write down the partial fraction expansion. We're going to have a over x plus bx plus c x squared plus 1. Okay, so for a quadratic factor, we don't just use a constant. We use a linear form, bx plus c. Okay, and that's equal to this should be equal to 2x plus 1. Okay, so you probably remember how to calculate A, B, and C. So I only look at the numerators and I try to test particular values of x. When x equals 0, I have a equals 1. Okay. Now let's take, I don't have any other obvious choice because there's only one root here, 0. So the other one I'm going to try is 1 and minus 1. So for 1, I have a times 2 plus b plus c equals 3. And for minus 1, I have a times 2 minus b, plus b minus c equals minus 1. So I have two equations. Oh, and a equals 1. So this is just 2 and 2. How do I solve this? So for instance, I can take the first, so I have b plus c equals 1, 3 minus 2. Therefore, c equals 1 minus b. And I substitute it here. So I have 2 plus b minus 1 plus b equals minus 1. Or b to b equals minus 2. B equals minus 1. And the third one, c equals 1 minus b equals 2. Okay, I found all the coefficients. And now I go back to the integral. So I have an integral of 1 over x dx minus x dx x squared plus 1 plus 2 dx x squared plus 1. So there are three integrals that I have to evaluate. All of them are quite simple. So the first one is just the log. Okay. The second one is a very, very, very easy substitution. So let's take u equals x squared plus 1, which means that du is 2x dx. So this guy gives me du over 2 over u, okay, which is 1/2 log u, 1/2 log of x squared plus 1. So I continue here with the minus. Okay. And finally, the last one is a known antiderivative. That's the arctangent. So I have plus 2 arctangent x plus c. Okay. So whenever I have a non-repeated quadratic factor, this is all I'm going to get. These three types of integration, all of which are quite easy. Okay. Let me give you a difficult, more difficult partial fraction thing. So x to the 4th plus 1 dx x squared plus 1 squared. Here we have a repeated quadratic factor, right? There's not one but two of these things. So the most important thing here is to remember what we do with this. So we're going to have a over x, obviously for the first one. So we are going to have x squared plus 1. Okay, that this is the repeated factor, and because it's quadratic, it has to come with its own little linear form, not just a number. What else do I have? I have to match the fifth order, so I have to have two more coefficients. 1, 2, 3, two more. So I'm going to have this factor to the power of 2, and it has to have its own linear form, like this. Okay? If I had a cube here, I would have one more, fx plus g divided by this thing cubed, and so on, right? Is everybody on board with this? So now we have to calculate, bring everything to the common denominator. And this is supposed to be equal to x quarter, 4 plus 1 divided by the same thing. Okay. So we have to find A, B, C, and D, and E. So only one choice is obvious, right? We have x equals 0. Everybody turns into 0 except the first term. So A equals 1. That's really easy. The rest are not so easy. So I'm going to have x equals 1, x equals minus 1. I don't have any other roots, and I need 5 equations to determine 5 coefficients. So I need 4 more. And I'm going to have x equals 2 and x equals minus 2. Okay. I'm going to skip the calculation because you end up with a system of equations for B, C, D, and E. Let me write down the answer. Okay. So B and C are 0 in this case. D is minus 2, and E is 0. Okay. So I want you to fill in the calculations at your own time. So what do we end up with here? We have an integral of 1 over x dx. Okay. B and C are both 0, so the second term is 0. And the third term is dx, so I have minus 2. X, and in the denominator I have x squared plus 1 squared. Okay. And again, the first term is just the log. The second term is an easier substitution. So you say u equals x squared plus 1. So this guy becomes du over u squared, or minus 1 over u. So I end up having a plus 1 over x squared plus 1 plus c, and that's all. Questions? Okay. So because I have a little bit of time, I want to go back to one of the examples that I already did. And I'm glad I can do this. So let me remind you, you already have this in your notes. This is about improper integrals, right? Comparison test. I asked you, is this converging or a diverging integral? Okay. So what we did was as follows, because I knew the answer. We said 6 plus sine x over x squared. We said that this is less or equal than 7 over x squared. And we calculated the integral of this. And this converges. The question is, how did we know to find a function that's bigger than this? What if we what if we bounded it from below? Because there is another application of the comparison test. One could show that if the given function is greater than something that diverges, then this is also going to diverge. So there are two ways to go about these things. You can either find something that's bigger than the given, or you can find something that's smaller than the given, and then see what happens. Okay. So, question?
So if the bigger was found to diverge, would you have to check the smaller one?
So if the bigger one diverges, it means absolutely nothing, right? Because it could diverge, it could converge. So you'd have to check on the other side. Okay. Or you could start, in this case, you could start with saying, oh, let's look at the smaller one. Okay, so what's a function that's smaller than this? Exactly, 5. So we can say that 5 over x squared is always smaller than this guy. Okay. And the reason, again, is the same. The sign goes between -1 and +1. So the smallest it could be is -1, and that gives me 5. It can never go lower than this. So in principle, we could say, OK, this function is always bigger than this. So if I could show that this diverges, then for sure this guy diverges. Now, if we started like this, what would we get? We check this function, this simple function, 5x squared dx. And by the same argument as before, we'll find that this guy, of course, converges, right? It has the second power, okay, converges. So in this case, we have shown that something that is smaller than this converges. However, it means nothing for the given integral. So if something that is smaller converges, doesn't give me enough information. In this case, we would have to go back and try to see what is bigger than my function, you see? So I guess my point here is that you don't know in advance whether this integral converges or diverges. So you should look from below and from above and see which one gives you an informative answer. If something that is lower blows up, then this guy is going to blow up. If something that is bigger than this converges, then this is going to converge too. And that's how you should think about it. So let me modify the original function. So here means nothing. So use 7 over x squared. Okay. So I modify the original problem. Let's consider the integral from 5 to infinity, 6 plus sine x over x dx. What's the difference? The denominator is x now, right? So maybe you can tell me now, should I find something that's smaller and prove that it blows up? Or should I find something that's larger and try to prove that it converges? Smaller. So exactly. So we say that the original function is greater or equal to 5 over x. Okay? Now, the integral of 5 over x dx, what does this do? You may remember that it diverges. Let me just do the calculation. This is the limit as t goes to infinity of 5 integral from 5 to t 1 over x dx. So this is 5 limit t goes to infinity of log x from 5 to t, or 5 limit as t goes to infinity of log t minus log 5. And I'm more or less done, because here I have a limit as t goes to plus infinity of a log t, and of course log very slowly, but increases to infinity. So this is infinity. So we can see that something that's smaller diverges, which means that the original function, which is 6 plus sine x over x dx, diverges too. Okay. Questions? Okay, so I want you to please take advantage of the extra office hours that the TA has tomorrow from 8:30 to 10:30. Please don't forget to bring your IDs and have a good night's sleep. Thank you.